Okay, so we're now on lecture 9 of the course, and so far we can divide the course maybe into, well, I suppose, 3 main chunks. The first one's just the introductory part, so let's forget about that. But from lectures 3 to, I guess, 6, we did things like the simplification of formulas and these various normal forms for formulas, some decidability results for theories, and the proof rules, which are ways of manipulating formulas to be able to reason with them. We could see a general theme there, as we were always concerned with practical things we can computationally do with, let's say, computation with formulas. I mean, it doesn't really summarize everything we were doing there, but computation includes, in this case, reasoning with formulas with the proof rules. It is kind of, even if there were some abstract mathematical methods being used, there was this concrete underlying theme there. Whereas in the last 2 lectures, so lectures 7 and 8, we were looking at model theory instead. And this is very much in the world of abstract mathematics, dealing with structures, which are sets with structure, which is why they're called structures. And we were talking about things like the cardinality of structures, and I'm trying to avoid cardinalities to a degree in this course. But anyway, we were talking about infinite structures, and it seems like far removed from computational considerations. So today, what we're going to do is a synthesis of these two, and perhaps surprisingly, techniques from model theory can be used to establish algorithms for example, and that's going to be the one application we consider today for deciding theories. So we're going to get decision procedures for theories using model theory in order to get them. And it's it's not very intuitive that one could do that, because this looks at first sight, the model theory looks at first sight to be so much in the realm of abstract set theoretical mathematics. So today, model theory, sorry, that's the wrong way around. Decidability via model theory is the theme. And then from next week, we're going to go into another phase of the course. We're going to have a 4-week block of lectures. So we're going to have weeks 10 to 13. And what we're finally going to embark on here is the theory of arithmetic, of the natural numbers, and Gödel's incompleteness theorems. And the teaching calendar has been very kind to us this year. So often when one's teaching a course, it's a struggle to fit in you can fit in 13 lectures or something like that if you're lucky, because lots of holidays interrupt the flow, and it's hard to schedule enough lectures around them. This semester, if you check the timetable, if we had a lecture every Wednesday, we would actually have 16 lectures. So there are 16. We don't have any holidays on a Wednesday or even on a Tuesday when you have exercise classes. There's a possibility of 16 lectures. I think that would be too much. But given that there is for once the opportunity, I am going to have the full 15 lectures. So just to say what's coming, following that, we're going to have the last block in weeks 14 to 15. And there I thought I'd cover something completely different, which is proof theory. So well, it's not totally different because we did proof systems in lecture 6 already with the Hilbert system and the proof system, but I want to do some more interesting proof theory, if you like, with a usable proof system and also some of the mathematical manipulations you can do with it. So my aim here is to do proof theory. I won't write it down, but we're going to do Genson's sequent calculus, and then Genson had, so we're going to learn in Gödel's incompleteness theorem, his second incompleteness theorem, that a theory cannot prove its own consistency, a theory of arithmetic, which is a very intriguing and thought-provoking fact. But one of the clever things Genson did was he did come up with a very nice combinatorial proof of the consistency of arithmetic. So in the last lecture, I want to, it's too much to cover the whole proof, but I want to give you some ideas about that. So first, Genson's consistency proof. Thing to say, well, I'm in this stage of summarizing. You may have noticed, so last week I forgot to put the LaTeX lecture notes online. I've done that for last week, but you'll see that not much of the material covered last week is in the LaTeX notes. Today, actually, the LaTeX notes are quite comprehensive, so I've already put those up, although I'm going to give a different proof in the lectures, in one case to the proof in the LaTeX notes. From next week onwards, I'm afraid there will not be any LaTeX notes. I may try to supplement with handwritten notes, but anyway, I did say at the start of the course that the lecture notes are not, the LaTeX notes are not going to cover the whole material. I always mean to write this next part up, but there's always something better to do. Or more pressing, I mean, not better, because this would be a very good thing to do, but more pressing to do. And once again, this year, I'm not going to have time to write it up. Okay, so are there any questions on that? Okay. So we're going to do decidability via model theory. So we've already met the notion of decidability, and I've told you a theory is decidable if we have an algorithm that we input sentences as the input to the algorithm, and it's decidable if we have an algorithm that, given a sentence, will tell us whether that sentence belongs to the theory or not. Because today the main topic is going to be decidability, we need to start, and also we're going to need to know more, as it turns out, more about decidability in order to properly tackle Gödel's incompleteness theorem. The reason for that is that Gödel's incompleteness theorem specifically applies to theories which have what's called a computable axiomatization. So we're going to need to know what it means to have a computable axiomatization. So for those reasons, I'm going to start now being a bit more careful about what's meant by decidability and those sort of things, and all related concepts from computability theory. Now, a few people in this room took a course on computability theory last semester, so this will be repetitive for them, except that I'm going to do it from a more abstract point of view today. So I'm not going to go, so the idea is what I'm going to cover now for, I mean, this is going to be at most the first hour, is going to be a high-level approach to computability theory that we can latch on to, even if we don't want to know what the details of a Turing machine or something like that are. But the idea is we want to be able to talk about algorithms dealing with inputs like formulas, but also other related inputs that we might have from logic. So I want to just in general consider abstractly a notion of we'll just use our informal notion of algorithm, meaning, if you like, some procedure that we could give some precise instructions for how to follow it. And for those of you who are experienced with computer programming, which is probably everyone, you can think of an algorithm as just something you could program. But we're going to consider abstractly algorithms dealing with different kinds of data. So an example of the kind of data we might be interested in is logical sentences. That's some data that if we want to do decision of theory, then that's the kind of data we're interested in. So we're going to have algorithms dealing with any appropriate form of data. And what do we mean by an appropriate form of data? Well, loosely speaking, the kinds of data that are relevant to what I'm going to talk about today are what we call discrete data. So basically, data that can be given as a finite string of bits, if you like, a finite sequence of bits. So we're going to consider abstractly algorithms dealing with discrete data. The data that can, if we want to be concrete, can be given by finite words of bits, binary digits, so 0, 1. And that will include numbers, sequences of finite sequences of numbers, terms over a countable signature, formulas over a countable signature, sentences over a countable signature. I won't bother to write them down, but all these things we can encode using finite sequences of bits. And that's not surprising because, with some programming experience, we know that we can perfectly well represent these things on a computer. And if we're representing them on a computer, we're always underneath. We're using finite sequences of zeros and ones. Okay. And the general abstract setting for the next bit of the definitions I'm going to now give, and we're going to even prove a few little propositions at this abstract level. So the general setting I'm going to have is we're going to have D is a set of kind of a global set, if you like, of distinguished data we're interested in. So it might be the natural numbers, or it might be logical sentences. And then we're going to, so D stands for data, and we're going to work with S, a subset of D. We're going to consider various properties that the subset S might hold, like, is it decidable, or it's something a little bit weaker than decidable, is it semi-decidable, and some other related properties. A subset. And we've already met the notion of decidability in the special case, on this course, in the special case of deciding a theory. But it makes sense at this more abstract level. We've got our global set of data. And we've got some subset of the global data. And we want to constrain to get inputs from the larger set. And we want to recognize whether or not something belongs to the smaller set. Potentially smaller set. And so just to remind you, but now in this general setting, so a subset S of D is decidable. And as I say, we're going to just have an informal notion of algorithm, but those who've done a computability theory course will know that one can make sense of this in We can make this precise in various ways, and they all turn out to be, all the sensible ways turn out to be equivalent. So a subset is decidable if there exists an algorithm that takes as input any element of the larger set D, so any little d belonging to the larger set D, and then is guaranteed to terminate with a response. So it can compute for some time. It might do some thinking, some calculating, and eventually terminates with a response with yes if D belongs to S, and no if D does not belong to S. So these things are great to have because you give it your input, you know it's guaranteed to terminate, you just need to be patient, you wait for the answer, and then you know whether or not your input belongs to the set. Of course, sometimes you need to be very patient, unrealistically so, like when people were first analysing the complexity of algorithms in the 1960s and 70s, they loved to come up with examples where you'd have to wait longer than the expected lifetime of the universe in order to be able to get the answer out and this sort of thing. Anyway, so you don't. So decidability is sometimes not practical. You need some complexity guarantees for it to be practical. But anyway, so it's a good first approximation that we're able to recognize the set S. Well, there's a weaker notion that's going to be important for us, and has already been mentioned in the course, I think. And that's the notion of semi-decidable. And it's a notion that arises naturally because we have the idea of algorithms computing in time. And they take some time to give the answer, and you need to be patient. And semi-decidability is you have a weaker guarantee. If your element belongs to the set, you're guaranteed that the algorithm will terminate, and it will give you the answer yes. But if it doesn't belong to the set, then you don't have any guarantee. So the algorithm might just continue computing, and you're just sitting there twiddling your thumbs and waiting for an answer. And you never actually get to know that the element doesn't belong to the set. You just know that you haven't yet got an answer from the machine. So this is called semi-decidable. So S is, so again, it's a subset of D, is semi-decidable. If there exists an algorithm, I'll just write an alg dot, that given any D in the larger set, any data item, little d in the larger set D of all data items, either eventually terminates with yes, with answer yes, if D belongs to the subset S, or in the other case, simply runs forever, or runs forever if D does not belong to S. And it's going to be, let's rub out the definition of decidability. I'm just going to make some very basic observations about these notions.
Excuse me.
Yes.
About the definition. Isn't it so that if it's not indeed, it can, in some cases, it can also output no? In some cases.
Yeah. So we could also make the definition so that if the set, if it didn't belong to, if the input did not belong to the set S, sometimes the machine could be more helpful and tell us no. We then get an equivalent definition of, I mean, the algorithm's different. We get more information from such an algorithm. It's better for us if we get that partial information. But still, the definition of the definition of semi-decidable is sorry, the definition. And that's easy to see because if you've got an algorithm that outputs no, you can modify it to get an algorithm that if it's about to output no, it just goes into a loop instead. So yeah, you can frame the definition in that way, but it's an equivalent. It gives you an equivalent notion of semi-decidable set. The proposition, which for those of you who've done computability theory, you'll know this stuff very well. But firstly, every finite set is decidable. Why? Well, if it's a finite set, there are finitely many elements. So you've just got an algorithm which is basically a sequence of if-then-else statements. If there are k elements, then you have k if statements. If you're this element of S, then yes. If you're this element of S, then yes, and so on. And if you're none of them, then finally no. Okay, so that's easy. So secondly, there exist infinite decidable sets. Infinite, like the set of natural numbers or the set of sentences or something like that. So obviously then the whole set itself is decidable. You always output yes. But thirdly, if S is decidable, then a fortiori it is semi-decidable, because you simply modify your yes-no algorithm to do what I said earlier. But if you're about to output no, you instead go into a loop. But the fact that there exist semi-decidable sets that are not decidable is not obvious. And this is a result in computability theory, which I'm not going to prove today, but let's just state it. There exist semi-decidable sets that are not decidable. And this is like the first important result of computability theory, basically using a technique called diagonalization. And this was proved independently by Church and Turing. So something we will use is the following result that tells us when a semi-decidable set is decidable. It characterizes exactly when a semi-decidable set is decidable and in a useful way. So this is another proposition. So S is decidable if and only if both S and its complement, where the complement here is of course D minus S, because D is our surrounding set, and all data items are both semi-decidable. And I want to give you a little argument for this, just to show that we can do things at this high level of just informal algorithms. Well, firstly, the left to right direction is obvious. You basically modify the algorithms by going into loops when necessary and switching yes and no sometimes. And I'll leave that for you to think about. The interesting one is that if S and its complement are both semi-decidable, then we want to get a decision procedure. I should have said when I defined decidability, we call an algorithm that checks whether, that performs the process of telling us whether an element belongs to a decidable set, we call that a decision procedure. So suppose S and S complement are both semi-decidable, how do we get a decision procedure for S? Well, the idea here is that we run the following algorithm. So given an input, little d belonging to the larger set, we want to know whether or not it belongs to S. Well, we have a semi-decision procedure for S. That's an algorithm which will return yes if the element belongs to S and run forever ever otherwise. And we have a semi-decision procedure for S complement, an algorithm that will run forever if D belongs, that will return yes if D belongs to S complement and run forever otherwise. We simply run those two algorithms in parallel and wait for one of them to give us a result. And by the fact that if the D belongs to one of these sets, you're guaranteed to get a yes from the definition of semi-decidability. And it must belong to one of those two sets because they're complements of each other. One of them will give a result. And of course, exactly one because the two sets are disjoint. So, and then just depending on which one eventually gives the result, you then return yes or no. So we simply, so I'm just going to write that at a high level. So run semi-decision procedures for S and SC in parallel and return yes or no according to which one holds. Okay. So it may seem from this that our notion of algorithm needs to include parallel computation. Actually, it doesn't. I mean, we are using parallel computation, but if we have just a sequential model of algorithms, we can still do the same thing in the sequential model. We just have to do what's called interleaving the two computations. So you do a step of one and a step of the other, and so on. Right. Make one other remark about semi-decidability. Which is a nice characterization of it. So let's put it like this. The following are equivalent for a subset we're going to characterize semi-decidability. So one is that S is semi-decidable. The second one is a very different looking property, which says that this is not the interesting case, which says that if S is non-empty, then we have a computable function from the natural numbers to D, whose image is S, or there exists a computable function f from the natural numbers to a set of data items such that the image, I'll write like that, or the range, the image of f equals S. So what this is saying is we can, by a computable function, enumerate all the elements of the set S, possibly with repetitions, and in general it's necessary to include repetitions because, for example, if S is a finite set, then you're obviously going to have some repetitions in here, but nonetheless we can enumerate all the items of S. And in fact, this property is so important that there's a standard name for semi-decidable sets that is basically named after this property. So semi-decidable sets are also known as computably enumerable sets, and that's because of this property. So because of this property, semi-decidable sets are also called computably enumerable, and in fact the empty set is also counted as a computably enumerable set, just to be tidy. I called computably enumerable sets which is often abbreviated as C.E. And the old-fashioned word for this used to be recursively enumerable, or recursively enumerable. And people used to say RB instead of recursively. So these are nowadays considered synonyms for semi-decidable. And there are also synonyms for decidable. So decidable sets is also called, they're also called computable sets rather than computably enumerable, computable, or in the old days, recursive. So maybe I won't talk through why this is the case, but you can if you've got a semi-decidable set that's non-empty, you want to get the existence of a function, you basically do this. We're going to construct the function as a sequence, a first element, a second element, a third element. And what we do is we enumerate, we assume we can enumerate all the items in D. That's normally easy, that the natural numbers or the sentences or something like that, we've got a very systematic way of enumerating those things. That's an assumption that I didn't make explicit, but about our notion of discrete data. So we've got all the items in D enumerated. We basically go through them one at a time and start running our semi-decision procedure on them to test them. Now, of course, that semi-decision procedure, we don't know how long we need to wait. So we start doing this in parallel. We started on the first one, we then started on the second one, started on the third one, and so on. And we just wait for one of them to terminate. And as soon as one of the ones we've already started terminates, we put that one in to our sequence. And then we carry on with other ones. But in order that we keep on enumerating the sequence, once we've put one in, after a certain amount of time, if we don't get any more information, we can repeat the one we've already put in just to make sure we're going to eventually give ourselves a total function. So there's a little bit of You have to be a little bit careful in how you define it, but anyway, that's the idea. And this is not a course on computability theory anyway. This is just to have some background material. Okay, so now I want to start applying these notions to logic. So this is as much as we're going to do abstractly about computability. And with this, we're going to now have a definition that is going to be important for today, but is also going to be fundamental in the next part of the course on Gödel's theorem. So this is to do with a theory having a computable axiomatization. So maybe it's, you know, we're going to have the notion of a computably axiomatized theory, and that is basically exactly, you know, you could probably write out a definition just from hearing the words computably axiomatized. And just to make sure we're all on the same page about it. So the idea of an axiomatization, we say that S axiomatizes T, the theory T. So now S and T are sets of sentences over some signature we've got. And by the way, when we're talking about decidability for a logical signature, we're always assuming the signature is countable. And if it's an infinite countable signature, we obviously assume that it's got some sensible representation using, well, anyway, you can represent infinitely many symbols using finite strings of bits, infinitely many different finite strings of bits. So S axiomatizes a theory T, where S and T are sets of sentences. If, well, obviously T is the theory of S. I think I've defined theory of a set of sentences, but in case I didn't, what we mean by this is the theory of the collection of structures where M is a model of S. Okay, I don't quite remember all the various incarnations of the concepts that I introduced in the early lectures. And we simply say that T is computably axiomatizable. Well, can somebody guess what the definition is? Yeah. If, well, what is S? So if there exists an S, that is computable. So if there exists a computable S, so remember, computable means decidable. But people never say decidably axiomatizable. So in this case, we always use, but it means decidably axiomatizable. So if there's a decidable set of axioms such that S axiomatizes T. So notice the set of axioms can be infinite. And actually, when it's finite, of course, if T has a finite set of axioms, then it's automatically computably axiomatizable because any finite set is decidable, as I already said. So if T is finitely axiomatizable, then it is computably axiomatizable. Okay. The computable axiomatizability is important because it's basically saying we can write down the axiomatization in some way. We can decide if a sentence is an axiom of our theory. That's an important property. If we can't decide if a sentence is an axiom of the theory, we're not going to be able to do that much with the theory. Except you might disagree with that because it wouldn't seem so bad to just say maybe we could, maybe we don't need decidability, but what about semi-decidable? Because as long as we've got a computably enumerable axiomatization, then we can, by this property here, we've got this computable function, so we can produce an exhaustive list of all axioms. It's an infinite list, but nonetheless we can generate all the axioms. So it's natural. So this is computably axiomatizable. That's the definition. It's natural to make another definition. T is computably enumerably axiomatizable. If there exists a computably enumerable S such that S axiomatizes T. Now, if you look in the logic literature, you will never find very much talk about computably enumerable, about computably enumerably axiomatizable, which is just as well because it's quite a mouthful. But the reason is, I mean, the one thing you will find is the following result, which is quite surprising. And once again, this is going to be an example of a proof that involves computability theory, that nonetheless we can prove, sorry, of a result that involves computability theory, but nonetheless we can prove at the abstract level at which I'm, at the abstract high level at which I'm talking about computability theory in this course. And that's the following theorem. The following, again, are equivalent for a logical theory T. And this is, really quite surprising when you first see it. Firstly, T is computably axiomatizable. Secondly, T is computably enumerably axiomatizable. And thirdly, T is just simply computably enumerable. As a set of, it is a set of sentences, and that set of sentences is itself semi-decidable. So that's our first main result for today. And we're going to prove this after the break. Okay, are there any questions? No, okay, so, all right, so the clock on the back wall says 1 minute past 5, so we start again at 16 minutes past 5. Okay, so we're going to start by proving this theorem that is basically saying we don't need the notion of computably enumerable axiomatizability because the easier to pronounce computable axiomatizability is the same thing. Actually, we don't even really need the notion of computable axiomatizability because we could just be talking about computably enumerable theories because they're the same thing. Nonetheless, people do like to talk about computable axiomatizability. And the reason for that is that in the context that people talk about that, it's often very natural to think about axiomatizations. And indeed, to show that a theory is computably enumerable, a very natural way to, and often practical way to do it is to come up with a computable axiomatization for it. So computable axiomatizability tends to be the nice property to work with. Anyway, so we've got 3 statements to prove equivalent. Actually, 2 implications are immediate. It's immediate that if it's computably axiomatizable, then it's, of course, computably enumerably axiomatizable because every computable set is computably enumerable. So 1 implies 2, it's immediate. But also 3 implies 2. 3 implies 2 is also immediate, because if the theory is computably enumerable, then how do we find the computably enumerable axiomatization? Well, you just take the whole theory itself as its own axiomatization. So the theory itself, you can have all the sentences in the theory as axioms. So 3 implies 2. Whoops. 3 implies 2 is also immediate. So to complete, I mean, because both of these go to 2, it still means we still need to go to the same destination. We still need to prove 2 implications. So we're going to prove 2 implies 1 and 1 implies 3. The most interesting one is 2 implies 1. And that's, we've got our computable enumerable axiomatization, and we need to come up with a computable axiomatization. So let S be a CE axiomatization of T. And we've got a set of sentences that are our axioms, and the property we have of them is that we can semi-decide whether a sentence belongs to that set S. How on earth are we going to convert that into an equivalent axiomatization where we can actually decide whether a sentence belongs? So what we're going to do is we're going to use the semi-decision procedure we have for S, and then we're going to apply some clever trick, which is known as Craig's trick, after the logician Craig, who came up with this idea. So we have a semi-decision procedure for S. So using this, we're going to define a new axiomatization. We're going to define a new axiomatization S prime. And the idea is, so a semi-decision procedure, that's an algorithm that will, given an input, as we know, eventually return S if the input belongs to, eventually return yes if the input belongs to the set S, otherwise we'll compute forever. And we're going to assume now, if we were using Turing machines or any other, we had a more precise notion of computability, we would have some model of computation on which we're running the semi-decision procedure. We're going to assume we can count the number of computation steps that the execution of a semi-decision procedure or an algorithm takes. So using that assumption, which is reasonable, however we define the computable model, we're simply going to define S prime to be a collection of sentences built from axioms belonging to S, but we're going to pad them out with enough information that allows us to decide that they belong to S, rather than just semi-decide. So we're going to pad them out by making an equivalent axiom where we consider the disjunction with false, which is of course equivalent to A, and then we'll conjoin that to a conjunction of trues. So this whole sentence is equivalent to A. We're going to put K many trues in where this belongs to the theory, this belongs to the set S prime if A is indeed an axiom in S, and also, so in the case that A belongs to S, we know the semi-decision procedure for belonging to S will halt with input A, and we include such an axiom if it halts in exactly K steps. Okay. So A belongs to S, and the semi-decision procedure for S halts on input A in exactly k steps. So this is then a decidable set, because if we want to decide if a sentence belongs to this set, we take the sentence and we look to see if it has this form at all. Is it some formula disjoined with a false and then conjoined with some? So we parse it to see if it looks like that. If it doesn't, we say no, because it doesn't belong to this set. If it does look like that, well, from the form that the sentence has, we see how many truths there are in the conjunction. That gives us k. We then run the semi-decision procedure for S for k steps, and we see whether it comes up with the answer yes. That's exactly k steps. If it does, then yes, we've got our axiom. If not, then we say no. That doesn't belong to the sentence S prime. So yeah, I'm not going to write all that down, but I've explained it. You can watch the video if that was too fast, or you can look in the later lecture notes for a bit more explanation. I mean, I explained it enough in words. So S prime is decidable and axiomatizes the same theory, as S, because every axiom of S gives rise to exactly one such axiom belonging to S prime, and it's clearly logically, this is clearly logically equivalent to the original A. Okay, so I think that's enough detail for 2 implies 1.
So why do we need the or false?
So I put the or false here just in case. I mean, we've got brackets, so maybe brackets, and I'm not quite really saying how to parse this, but just so we can count the number of truths and unambiguously get the number of.
A ended.
Just in case A ended with an and true or something like that. So just to be absolutely in most logic textbooks, they're not as fussy as me. So and they don't tend to have true. I mean, anyway, but there are many ways of doing it. But it was just a parsing issue. Right. So good question. So the other one we're going to do is 1 implies 3. So suppose we've got a computably axiomatizable theory. We want to get that it's computably enumerable. We simply, so to get it's computably enumerable, by the characterization of semi-decidable sets as computably enumerable sets, it's enough to define a function from the natural numbers to sentences that lists all the axiom, lists all the sentences in the theory. So we do the following: we construct a function from natural number to sentences whose image is S, sorry, is the theory of S, which is T, as follows. And we've got our proof system. We simply enumerate, we systematically search through all possible proofs that we can construct using our proof system. And when we've got a proof, we use the decidability of the axioms to check whether all the assumptions we used in the proof belong to the set of axioms. And if so, we say, aha, we have found a sentence that belongs to our theory. And once again, we're constructing this as a sequence of one formula at a time. And whenever we find a new proof that we hadn't considered before, whose assumptions all belong to the theory S, which we can test using decidability, we add the conclusion of the proof to our list of sentences. And then we go on to the next one. And we carry on like this. So we do this, we enumerate all proofs. And check each proof to make sure to ensure its axioms belong to S. So for that for that check we're using decidability. And if so, we add the conclusion of the proof to the enumerated sequence. The conclusion of the proof to the enumerated sequence.
Yep. I guess by the definition, if we're going by the definition, I guess we're also using completeness here, right? Because we're checking the syntactic.
Yes, we're using completeness to know that every sentence in the theory will be bound by will be the conclusion of some proof. Yeah. So indeed we're using completeness. Yeah, good point.
And soundness as well.
And probably and soundness as well to make sure we don't actually add anything that's not in the theory. Yep, so good. We're using soundness and completeness. So I may quite often from now on use soundness and completeness without explicitly saying so every time, but it was great for you to point these things out. Right, good. Okay, so we've got this notion of computable axiomatizability. Maybe I'm going to kind of do things in a different order from my notes. So maybe it seems natural to me now to immediately move on to how we're going to apply this notion of computable axiomatizability to get decidability using a model theoretic result. And what we're going to do, so let me go to the main statement of the theorem. Things quite backwards from my notes. So I want to now, in the rest of the lecture is going to be kind of more applied, if you like, and we're going to prove some theories are decidable. And how on earth is this related to proving theories are decidable? Well, it's not so far off. I've rubbed out the statement of the theorem because we're establishing that theories are computably enumerable here. So we're getting semi-decidability. So to get decidability, we only need to get that the complement of the theory is semi-decidable. And actually, there's a condition that often arises that allows us to do that very easily. And then we're going to use the following. We're going to state this as a theorem, and this is by Janicak, I think. Yep. Janicak, or I'm not sure if it has some diacritical to see or not, or which country Janicak came from. Anyway, Janicak's theorem says if a theory G is computably axiomatizable, again we could say equivalently computably enumerable, but in practice it tends to be easy to show that by coming up with a computable axiomatization. And there's one more property, complete. So remember, complete means that for every sentence, either the sentence or its negation belongs to the theory, then T is decidable. And this is really easy because we know that for decidability, it's enough to show that T and its complement are both decidable. Oh, sorry, they're both semi-decidable. Well, T is semi-decidable by previous result. So, because that's equivalent to being computably enumerable, computably axiomatizable. And what about the complement? The T complement is also semi-decidable because sentence A belongs to T complement. So if and only if, obviously, A does not belong to T. If and only if, because T is complete, not A belongs to T. Assuming T is consistent. So this is if T is consistent. But we can semi-decide whether not A belongs to T, because we can semi-decide membership of T. We just give not A as an input, and we wait to see if we get yes as an output. Okay, so this is clearly semi-decidable. Meaning for an individual property means our algorithm, we have the algorithm that will terminate with yes if this is the case and run forever otherwise. So just to say, so the proof here is using the assumption that T is consistent, but we don't need that in the theorem, because if T is not consistent, then obviously T is computable, computably axiomatizable and complete, and obviously T is decidable. So the theorem is still true in the case of an inconsistent theorem.
Is this orange circle equivalence not completeness?
Sorry?
Is this encircled orange equivalence not completeness?
It's not to do with completeness of the proof system. It's
completeness of the theory.
It's to do with completeness of the theory. Yeah, it is. I mean, yes. Sorry, it is. It also involves, of course, completeness, but it also involves consistency, because if the theory is inconsistent, not A will always belong to T, but A will also belong to T, but it will still be complete. So this is consistency plus completeness there.
Excuse me, I may be forgetting the definition of completeness a bit.
So completeness says for every sentence A, either A or its negation belongs to the theory.
Okay, but then an inconsistent theory cannot be complete.
But it's not necessarily exclusive of.
Oh, okay, I thought it was.
Yeah, okay.
But here it's only completeness, right? Because
No.
not for the other direction as well. Yeah, sorry.
No, it's consistency and completeness. Yeah. Good. Anyway, so simple result, and that's useful. So if we've got a computably axiomatizable theory, which is something we quite often have, because we have nice mathematical sets of axioms that are normally, we give them, often they're finite, they're given as a simple list. So we have a nice set of finite axioms. So all we need to do is to be able to find out if our theory is complete, and then it's decidable. And this is where we haven't used the model theory yet, but this now is where the model theory comes in. So how do we establish? So a nice way of establishing completeness is provided by model theory. This is what I think is the really nice bit of theory in this lecture, because it also brings us to an important concept in mathematics. So to establish decidability, we need to establish completeness. Model theory helps us establish completeness. And this is going to rely on the following notion. We say it's about when a theory, so model theory gives us a handle on theories in terms of their models. We're interested in what the structures are that model a theory. And in some very nice situations in mathematics, it turns out that all the models of a fixed cardinality are all isomorphic to each other. And this is called categoricity. And there's basically only one model up to isomorphism at some cardinality. So a theory T, let's just say T, is said to be. Now, this course is not about cardinalities, but still I'm going to put a kappa in here just to be general. In the LaTeX notes, it's not there. So special case will be when kappa is aleph naught, which is the cardinality of countable infinity. And then people actually, rather than saying aleph naught categorical, they tend to say omega categorical. So or more restrictively, so let's say respectively omega categorical if for every two models of cardinality of the theory of cardinality kappa are isomorphic. So for every two m and m prime, we have where the cardinality of m is the same as the cardinality of m prime, so the sum bijection between their underlying sets is equal to kappa, or sorry, this should say not rep, should say RSP dot, which is short for respectively. And why I'm saying respective is because I need to make the respective condition here. So respectively that these have the same cardinality, and this is aleph 0. So it's countably infinite. For every two m where this holds, we have that m is isomorphic to m prime. Okay. So it's an important definition.
Excuse me. So inconsistent theories are zero categorical. That is the definition, I think. Yeah, maybe.
Inconsistent theories are categorical at every cardinality kappa, just because they don't have any models at all. So just vacuously, this universal quantification is always true. So they're decidable. Oh, sorry, I haven't related it to decidability, but the theorem. So maybe I'll prove the theorem, and then we'll go to the examples of categorical theories. So the theorem. Can anyone guess what the theorem is? The theorem is that if T is kappa categorical, then something holds. So omega is just a special case. If it's omega If it's omega-categorical, then it's kappa categorical, but kappa equals out 0. Anyway, if T is kappa categorical for some infinite kappa, then it is complete. It's important for kappa to be infinite here. I'll let you think about why it fails for finite cardinalities. Okay. I'm in a mood for drawing red boxes around here today, so that's sort of to flag what's important. So the point is, if we have a computably axiomatized theory, which we nicely have often because we have the axioms, then if we can show it's kappa categorical for some kappa, we have a decidability result. Okay, so proof. So let's do the omega case first, and then we'll do the general kappa case. Okay, so proof if T is omega categorical. So maybe it's a good time to just have a little peek at my notes. Aha! I forgot the condition as well. So actually, rather than just being kappa categorical for some infinite k, that's not enough. We require that if T has no finite models, and then it's complete. And this theorem is due to Vaught. Should have said that. Right. So it's very easy. That M and N be two models of T, not necessarily of the same cardinality. Substructure theorem. Always today assuming we've got a countable signature, because we're fundamentally talking about decidability of things. So this should have also been said. I mean, I did say it at the start, but it also applies. It's also required here. Actually, what we really need for this theorem is T has a signature of cardinality less than equal to kappa. But in the case of omega, that's a countable signature. So let M and N be two models of T. By the countable elementary substructure theorem, both of them have elementary substructures of that are countable. Because they're necessarily infinite, because T has no finite models. By the countable elementary substructure theorem, CEST, we have remember this is the notation for elementary substructures, and N prime, elementary substructure of N, that's a countable. We have countable okay. And by omega categoricity, N prime and N prime are isomorphic. Okay, but if you've got an elementary embedding, then the two models are elementary equivalent, meaning they satisfy exactly the same sentences. Also, if they're isomorphic, they satisfy exactly the same sentences. So remember the notation for elementary equivalence, we have that m prime is elementary equivalent to m. Oh, sorry, let's do it like this. M is elementary equivalent to n prime, which, because they're isomorphic, is elementary equivalent to n prime, is elementary equivalent to n. Okay, so all models are elementary equivalent. So if you take any sentence A, it's either true in all models or its negation is true in all models. So for any sentence A, either A is true in all models or what A is. In the first case, A belongs to T, because this is all models of T, and in the second case, not A belongs to T. In the first case, because T is the theory, any theory is the theory of its models, just by the definitions in lecture 2. So in the first case, A belongs to T. In the second, not A belongs to T, so the theory is complete. Okay, so this is the proof for omega-categoricity. Is essentially the same, only you start off with two infinite models. All models are infinite, m and n. And the point is, we use, if the cardinality is smaller than kappa, you use the upward Löwenheim-Skolem theorem that I mentioned a couple of lectures ago. If the cardinality is greater than kappa, you use the downward Löwenheim-Skolem theorem. Either way, you get either elementary substructures or extensions of cardinality kappa, which are then isomorphic by kappa categoricity, and then the same argument applies. So just to say the general theorem, and really for this course, only the countable theorem is needed for say the oral exam. I just wanted to make remarks about the general theorem so we know where we stand with respect to what's in the more advanced logic literature. But it's basically the same proof, just using the downwards and upwards Löwenheim-Skolem theorem. So for the general case, the general kappa case, use the downward and upward Löwenheim-Skolem theorem. Okay, so let's think about where we can apply this. So does anybody know any nice categorical models? Because this is something that also you see in algebra, in general algebra. It doesn't really need the notion of logic to be, the notion of categoricity doesn't really require logic because it's about isomorphisms rather than about, I mean, this application uses logic, but has anyone seen any interesting examples of?
Well, the reals are
Complete ordered field.
yeah.
Okay, so a complete ordered field is categorical in set theory with so it's not a first order axiomatization, but in set theory proves it's, but no, that's a good example. It doesn't quite fit into our setting because it's not a first order axiomatization. Okay, so a really nice one. A nice example is consider the theory of over the complex numbers over our favorite signature, so the signature of a ring. So this is the first order theory of an algebraically closed field of characteristic zero. So the first order theory let's say of algebraically closed fields of characteristic zero. And this is categorical in the cardinality of the continuum. So 2 to the aleph naught, categorical. And this can be proved using algebraic techniques. It's not a very, very hard result. I mean, I'm not going to do it in the lecture. We've got a countable signature because it's only got 4 symbols in it. And therefore, we haven't shown that it's got a computable axiomatization. So there is some work to be done there. We know it's easy to find the axioms of an algebraically closed field of characteristic zero. They're just the axioms for a field together with the axioms for every polynomial as a root, together with the characteristic zero axioms. So it's easy to find those axioms. It's not actually. No, that's enough. Because then by this categoricity result, we know those axioms are complete. Okay. And then it's necessarily so it's actually the starting place should be with the theory of algebraically closed fields of characteristic zero. That's 2 to the aleph naught categorical, therefore that's complete, and therefore that is the same as the theory of it's complete. This is clearly a model, and therefore it is the theory of this model. Okay, so we have then the theory of the complex numbers with the field structure, well, the ring structure that we can of course define the field structure from it is decidable from this. So modulo an algebraic result. So this needs an algebraic proof. So we get a nice decidability result for the theory of complex numbers, of the field of complex numbers. So theory of complex numbers is decidable. Okay. So I want to do a much more straightforward example, just so you see an actual proof of categoricity. And the straightforward example is one that you've already proved the theory is decidable in one of the exercise classes when we did quantifier elimination. But anyway, now we get a different proof. So, second example, theory of what's called dense linear orders. Without endpoints. There are various variations, I think some of which you considered in the exercise class, but anyway, this is the kind of the classic one in which you have dense linear orders without endpoints. So here we have the signature is just the strict binary less than relation. And we're going to, again, so here, as I said, the right starting point was the theory, was the axioms for algebraically closed fields. And then we derived that we have the theory of the complex numbers at the end. the right starting point here of the axioms for a dense linear order. So these are they're of course all universally quantified, so that the axioms for a strict linear order. So it's linear order, so x is less than y or x equals y. Dichotomy property holds, as it's called, or y is less than x. X is less than y, x equals y, or y is less than x. And then we have the denseness property, which says that the density property, rather, that if x is less than y, there exists a z between them. And we have there are no endpoints, so there always exists a y less than any given x, and there always, whoops, let's make it a correct formula. Exists a y such that y is less than x, and there exists a y greater than any given x. X is less than y. Okay, so these six axioms that you've seen before, and the theorem about this so it's certainly a theory that has no finite models because of any one of these three axioms gives us any one of these three properties gives us that we have no finite models. Because we don't have endpoints and we have the density property. So that's three different ways in which finiteness fails. And the theorem, so this is the theory of DLO. And the theorem, which is actually due to Cantor, is, does anyone know what the cardinality is with respect to which this is categorical? Omega-categorical. So it's countably categorical. So in other words, any two countable dense linear orders are isomorphic. Now, this is a very classic result in mathematics, and so probably you've seen proofs of this before, some of you. So just out of interest, hands up if you've seen a proof, you know a proof that any two countable dense linear orders are isomorphic. Okay. I'm going to prove this, but just briefly, and then we'll go on to a different application of model theory for decidability in the third hour. Okay, are there any questions before we pause? Right, I shall pause the video. Okay, so for the last hour, I want to begin with a proof of Cantor's theorem, which, of course, he did not formulate as the theory of dense linear orders is omega-categorical, but he just formulated as, which is equivalent, any two countable dense linear orders are isomorphic. So there's a written proof of this in the LaTeX notes, so you can read that. So rather than having another written proof on the board, what I'm going to do is just do a proof by picture, so you can basically understand the idea of how to prove this, but I won't write all the accompanying words. So this is something for you to follow as we go, basically. So we've got two countable dense linear orders, and we want to prove they're isomorphic. So the first one, it's a linear order like this, so we might start drawing it. It's going up the board, it's going up in the order, going down in the order, it's going down the board. Of course, the picture is not very good because it's a dense linear order, so wherever there's a gap here, there's something between it, and then when there's another gap, there's also something between that. But nevertheless, that's the best we can do with a finite number of symbols. And we've got another countable dense linear order on the right, and we want to establish some isomorphism between them. And because they're countable, they're necessarily infinite, we can assume that that the elements are enumerated. So each one has an index, if you like, from its position in the enumeration. So we've got a 0 element, a 1 element, and so on. And the way we're going to establish a bijection between them is we're going to do what's called a back and forth construction. And we're going to, so we establish the bijection where we start on the left-hand side and we make a connection to the right. And then we go back again. So that's the fourth, if you like, and then we go back, we stay on the right, and then we go back to the left. So what we do is we pick on the left-hand side, they're enumerated. We pick the first one in the order that we haven't yet connected to something on the right. So suppose this is element 0 here. And we connect that to something on the right. And for the first step, we can just connect it to element 0 on the right, which maybe turned out to be this one. Okay, now we're on the right. We go to the first one, the smallest element on the right that's not yet been connected to something on the left. So suppose that's element 1 up here. And we need to connect that to something on the left. So all we need to do is find an element that respects all the connections we made so far, which means it fits between any existing lines we have. So at the moment we've got one line, so the only constraint is we're not allowed to map to something that we're not allowed to cross lines here. So we're not allowed to map to something down here. So we just need to map to something above 0. So let's map it to here. In fact, you might always take the smallest element here that turns out not to, that is consistent with what's been done before, which is, yeah, who knows what that was, but let's suppose it was one, but this is misleading because it could be anything. But I'm going to suppose it's 1 for the following reason, because now we again pick the smallest element that's not been connected to anything, which is 2. So we need to find 2. Actually, it turns out 2 is one of the elements in the middle here. So I wanted this to be 1, so because that was the only way I could get the smallest element to be in the middle here. So now we now use element 2, and we've got, it needs to map to something above here, and so we go, it needs to be above the line, the highest line below it, and below the highest line above it, and we map to the smallest element here that satisfies those constraints, which happens to be, so 2 gets mapped to here, which happens to be, in this case, whoops, sorry, that's supposed to be an orange line. Doesn't really matter, which happens to be element 15 here. Okay, now we go to the smallest one, which is now 2, which hasn't been connected. So 2 turns out to be here, and we connect to something consistent, which turns out to be element 5, which is here. And so we connect 2 to element 5. And now we look for the smallest one here. We've got 0, 1, and 2, and 5. So we look for 3, which turns out to be up here. And we connect that to something which turns out to be element 2 up here. Anyway, but basically, every time we just take the smallest element that's not connected, you find something consistent with it, that's consistent with what you've done before, and you connect it. And we're building up a bijection. And it's going to be a bijection because every element on the left will eventually be considered, because we're always taking the smallest one that's not yet been included. And similarly, every element on the right will be considered for the same reason. That's why we do the back and forth, to make sure we include all elements. And just the way we're constructing it, we're being consistent, so we get to bijection. So we get to order preserving bijection. So that's as much as I want to say. Is there anything not clear about that? Proof by a picture. Okay. Anyway, it's a very nice property. For example, it implies that as ordered structures, the dyadic rationals, those that can be written as fractions with a power of 2 as denominator, are an isomorphic ordered structure to the rational numbers, which are also an isomorphic ordered structure to the algebraic numbers, which are another countable dense linear order of reals. If you want to consider what direct isomorphisms between any two of those sets would look like, then good luck to you. So it's a very simple construction, but in the end, relatively, it's not a totally trivial result. Okay, so this combination of two theorems, Janicak's theorem that says that if we've got a categorical theory, hang on. If we've got a computably axiomatized complete theory, then it's decidable. And Vaught's theorem that says if we've got a categorical theory, then it's complete. A categorical theory with only infinite models, then it's complete. It's a very powerful way of establishing decidability of theories that have infinite models. Not all that only have infinite models. Not all theories only have infinite models. So what do we do with theories that also have finite models? So the last part of the lecture is going to be an example of dealing with such theories. And this turns out to be a very powerful technique, not just in first order logic, which is what I'm going to talk about today, but also in many other logics like it's used very much to establish the decidability of modal logics. For example. And this is something called the finite model property. So we say theory T is the finite model property if whenever A is satisfiable by a model of T, whenever a sentence A is satisfiable by a model of T, it is also satisfiable by a finite model of T. This is useful because it turns out if a theory is finitely axiomatizable and has the finite model property, then it is decidable. The theorem, this is Harrop's theorem. If T is finitely axiomatizable and has finite model property, then it is decidable. Thing to remark here, so if we can establish the finite model property, so it's again a model theoretic property, it's a property about models, we have another technique for establishing decidability. And obviously the finite model property clearly only applies this disjoint class of applicability to the previous results, because this will only apply when we do have finite model. When we do have a lot of finite models of M rather than no finite models of M. So the remark to make about this is that here we're saying finitely axiomatizable rather than computably axiomatizable. It's not generally true for computably axiomatizable theories. This. And for those of you who've done some computability theory, it's not that hard to find a counterexample. So, I'll let you, if anyone wants a challenge, then, and you know some computability theory, then I'll let you think about finding an example of a computably axiomatizable theory that has the finite model property that's not decidable. All I'm going to do here is we're going to prove this now, and I shall remark on where we use the fact that the axiomatization is finite in the proof. Okay. So the proof is, I'm just wondering whether I can manage it without my notes. Let's try. So the proof is, once again, we're going to establish that both the theory T and its complement are computably enumerable. So are both semi-decidable. So we have T is semi-decidable, again for the same reason as before, because if it's finitely axiomatizable, then it's computably axiomatizable, and we have the result that's saying computable axiomatizability is equivalent to semi-decidability. So because finitely axiomatizable. So we just need to show that the complement of T is not semi-decidable. We show, is semi-decidable. We show the complement of T is semi-decidable. So in other words, given a sentence A as input, we want to semi-decide. So given A as input, we want to semi-decide, that is, we want a finite algorithm that's going to say yes in the it will eventually say yes in the example that A does not belong to the theory T. So we want to semi-decide, get that information that A does not belong to the theory T. Well, how can we show that A doesn't belong to the theory T? We can find a model of T that satisfies not A. Now, if there exists a model of T that satisfies not A, by the finite model property, there exists a finite model of T that satisfies not A. So the idea is we're going to just enumerate through all possible finite models of A and check them to see if we find one in which not A is true. And if we find one, then we say, yeah, A does not belong to the theory T. So we enumerate through all finite models of the theory T. But how do we do that? Well, we've got the signature, so we know how to. So we're now in the realm of a finite signature. That's important. So I keep on forgetting to say the constraints on the signature. Right, so we can enumerate through all possible structures for the signature. Because finite structures for the signature, because a finite structure is a finite set together with some interpretations of the functions and relations symbols on the finite set. Of course, it doesn't matter what we call the names of the elements of the finite set, so we can restrict ourselves to finite sets of the form 0 up to n-1 for some natural number n. So we enumerate through all finite structures with domain of the form finite structures M, curly M, with domain of the form, the domain meaning the underlying set, M is, let me write the square brackets of N for the canonical finite element, the canonical N element set. So sorry, this is structures curly M here, looks a bit messy, but anyway, the domain. So we can certainly enumerate through all these structures. And then for each one, for each such M, we check that M is a model of the axioms of M is a model of S, where S is the finite axiomatized or a finite axiomatization. Okay, and this is the place that we need to have a finite axiomatization. Because we need finite axioms because we want to check M satisfies every one of the finite axioms. So we can check this because to check if a first order formula holds in a finite structure is simply a matter of, for every quantifier, you go into a for loop and you check through all the finitely many elements that the property holds. So you have, if you've got like a whole load of nested quantifiers, you have some nested for loops. And but anyway, it's an easy algorithmic property to check if a first order sentence holds in a finite structure. So here we're using the finiteness of the axiomatization, and then in the case that M is a model of S, if so, we return yes. So our output, if also the formula, the sentence not A is true in M. So in that case, we've shown that A does not belong to the theory T. If not, we carry on with our search. Otherwise, continue with the search through finite structures. Okay, and because so we were only trying to define a semi-decision procedure, so that's all right. We'll go through all the structures of size 1, then all the structures of which there's only one, all the structures of size 2, all the structures of size 3, all the structures of size 4 systematically. There are only finitely many for every size. Yes, combinatorially horrible, but nonetheless, slowly but surely, one eliminates finite structures and one systematically goes through. We only need a semi-decision procedure. If there is a finite structure in which not A holds, we will eventually find it. Otherwise, we just continue the search, and that's fine because the semi-decision procedure does not need to return an answer. So this works precisely because T has the finite model property. Because T has the finite model property, which means if not A holds in some structure, in some model of S, then it holds in a finite model of S. So we will eventually find a finite model in which not A holds. Okay.
Excuse me. So I'm guessing here that we're just taking all of the of cardinality n is like in a group of like we're treating it as one model because theoretically there are infinitely many models.
Sorry, we're not treating it as one model. We have many models of size n. There'll be huge numbers.
Yes.
But for each n, I'm restricting to the model whose underlying set is, this is the set of numbers 0 up to n minus 1. Okay, so indeed there are infinitely many different sets of size n, but I'm only considering one of them because it's, as I said, it doesn't matter what we call the elements in the set. Yeah, so that's the point. Yeah, so that was addressed here. Good. Okay, so that's Harrop's theorem. The first application of Harrop's theorem is the theory of the empty signature that we already did in the first lecture on quantifier elimination. It is easy to prove that that has the finite model property. And then we get another proof of the decidability of the theory with the empty signature. That's not very exciting because we already had a result. The only thing that's nice about it is we avoid like that huge formula quantifying over partitions here. But on the other hand, we have an equally inefficient, or probably an even more inefficient decision procedure here from checking all the finite models. Okay, so the application of Harrop's theorem I want to show is what's called monadic logic. So that's an extension of, so that's the case of when we have logic with a signature which isn't empty, but we only have unary predicates. We only have predicates with one argument. It's called monadic because like mono for one, with monadic logic. Nothing to do with monads in the sense of category theory. Monadic means here relations of arity 1, so predicate symbols of arity 1. So monadic logic we're going to have a signature with some finite number of predicate symbols, each one a unary predicate symbol. So this is the sort of, we're colouring elements of the set in K colours, if you like. But actually, you could have several different colours applying to the set of the same element. Of course, the predicates might overlap. So it's more general than colour. But with no graph structure, because you can't have a binary relation. But every PI has arity 1. And the theorem is monadic logic has the finite model property, therefore validity for monadic formulas, monadic sentences is decidable. So the finite model property is often abbreviated as FMP, especially in modal logic. Hence, validity of monadic sentences. Well, let's not make that part of the theorem. That's a consequence of the theorem because of Harrop's result. So hence validity of monadic sentences is decidable by Harrop's theorem. Okay, so in the later lecture notes, there's one proof of this result. In the later lecture notes. And that proof has the property that, we need to establish the finite model property, so we need to show that if a monadic sentence has a formula, then it has if a monadic sentence is satisfiable, then it has a finite model. And the proof in the LaTeX lecture notes gives a bound on the size of that finite model property, of that finite model. People sometimes call this the small model property, if you have an explicit bound that's no worse than some iterated exponential or something like that. People call it the small model property, even though iterated exponentials are not very small. anyway, so the proof in the lecture in the LaTeX notes establishes this explicit bound. I'm going to give a different proof here, which doesn't establish the explicit bound, but is a bit easier and is maybe better for a lecture. And so actually the proof I'm going to give, there's an exercise in the LaTeX notes that suggests as an exercise doing this proof. So that's so you don't need to do this exercise because I'm going to do it for you. So the proof, so we give the proof. We instead follow the idea anyway. Right, so we want to prove that if a sentence in monadic logic has the finite model property, has a model, then it has a finite model. I didn't realize it was already 6:45. Course in previous years, and I've never managed to fit this proof into a lecture. and today I somehow thought I was doing okay, and I was going to be but it's too long for 15 minutes, and I don't see the point in getting started really, because one needs. Only getting halfway, it doesn't really do anything. So what I shall do is let you enjoy the proof in the lecture notes, let you for yourselves do exercise 9.8 in the lecture notes, and as in previous years, I'm going to say the proof of this theorem is not exact. So it's up to you if you want to do that. But I'm sorry, I really. I was just enjoying my cup of tea and sort of feeling tranquil and not rushing, and obviously that was a mistake. So I think, given this, probably the best thing to do is to end now and to just say, enjoy the lecture. If anyone would like to spend the next 15 minutes doing something, then you feel free to ask questions now. Are there any questions? No. Okay, good.